Welcome to the video demonstration of Big Cloud Fabric container networking with Kubernetes container orchestration. I plan to show the demo in two parts. First, I will demonstrate how Big Cloud Fabric P+V physical and virtual fabric solution with Kubernetes integration enables the dynamic networking for application containers as and when they are deployed through Kubernetes. In second part, I will demonstrate visibility and troubleshooting aspect of container networking using Big Cloud Fabric. For the demo, we'll be using two-tier distributed application called Guestbook. This is one of the Kubernetes demo sample application, which uses simple PHP, web frontend, and Redis database as the backend. Application logical topology is shown on left. The physical topology used for the demo is shown on right, which has two rack topology hosting the Kubernetes cluster nodes. Kubernetes cluster has one master node and two Kubernetes worker nodes, which are physically connected to the BCF fabric. From container networking perspective, Kubernetes master is installed with Big Cloud Fabric agent, which communicates with Big Cloud Fabric controller regarding all container endpoints orchestrated by Kubernetes on the fabric. Kubernetes worker nodes are installed with Switchlight Virtual and Big Cloud Fabric CNI plugin, which implements the container network interface specification. Let's look at the setup before deploying application. This is the BCF controller web interface. Let's look at the fabric view to look at the physical topology used for the demo. It's two rack leaf spine topology. Two Kubernetes worker nodes are shown at the bottom of the screen running virtual switches. These Kubernetes hosts are auto-detected by the controller as you connect the host physically to the leaf switches. Let's look at the configuration required on the BCF using the tenant page. I have kube demo tenant configured with two logical segments, one for Kubernetes control traffic and other for container application traffic. The spawned container will be added to this segment, and containers will be dynamically assigned with the IP address from the subnet configured on this segment using BCF Kubernetes integration plugin. Architecturally, Kubernetes namespaces maps to BCF segments. Depending on your application network requirement, one can have multiple Kubernetes namespaces, so containers can be spawned in different segments based on which namespace they belong. BCF endpoint page shows all the endpoints. It is filtered to show endpoints on tenant kube demo. Currently, we have only two endpoints in control segment for two Kubernetes worker nodes. As part of the demo, we will deploy containerized application and see how we learn and update the endpoint table with container endpoints. Here are the steps for the first part of the demo. Orchestrate and deploy the microservice application Guestbook using Kubernetes. Verify BCF controller for container networking, and then access the Guestbook application using the web frontend and add some guest comments. Verify it gets stored in database and accessible from other frontend containers. Before deploying application, let's look at the application service specification defined in the YAML file. Application as service Redis master defined as the backend, which is serviced on TCP port 6379. One instance of master node is deployed with container image specification as shown. Similarly, application backend service Redis slave defined to have two instances, which is serviced on port TCP 6379 as well. This is the front-end application service for app Guestbook, which is serviced on container port 80 and node port 30300. In this demo, application service is exposed through the Kubernetes worker node port. In production environment, it will be deployed using load balancer. Front-end service configured to have three instances. This is the container spec defined for front-end service containers. Before deploying application with defined spec, let's do Docker PS. Look at the containers on Kubernetes worker nodes as we deploy the application. On master, use kubectl create with the application YAML file to deploy application. As you initiate the application creation, in the background, Kubernetes master would schedule the application pod containers on worker node to create defined services. As containers are created, BCF plugin, BCF agent, and BCF controller take care of networking for containers by providing IP address, segment, and attach the container interface to the BCF virtual switch. Now, if you look at the services on Kubernetes master, you would see new services created for application frontend, backend Redis master and slave services with virtual IP and ports associated with that service. On worker nodes, new application containers are spawned using the Docker. Now, if you look at the BCF controller endpoint table, it is updated with new container endpoints which are attached to the BCF virtual switches. The endpoint table provides detail on the container segment, name, IP and MAC, virtual switch or Kubernetes worker node where it is spawned, and virtual NIC where it is connected. Now let's access the deployed guestbook application and some comments to the guestbook which would get stored in the Redis database. This is the application front-end service. Let's add a comment on to the guestbook. Welcome to the guestbook and submit. It gets saved in the database. Let's add comment guest1. Now let's use the same guestbook application from other front-end instance on another node 10.2.18.52 port 30300. This should have the updated guestbook with earlier comments, as this is getting this info from backend database. Now let's add comment on this front end and see it gets updated on the front end application access to first instance. It should see updated guestbook, and you can continue to use this guestbook to add more comments. From networking side, the application traffic between front end and back end is forwarded by BCF P+V fabric on given segment. This is how Big Cloud Fabric P+V solution with Kubernetes integration enables the container networking. Let's look into the visibility and troubleshooting aspect of Kubernetes container networking using Big Cloud Fabric. BCF test path feature enables the troubleshooting communication issues between any two endpoints, in this case containers. You need to provide the source endpoint. Let's take application front-end container as source endpoint and select Redis master backend container as destination endpoint and have TCP port 6379 as application port, which is the port used by front-end to access backend database. Let's run simulate mode to see the logical and physical path between these two containers. Logical path validates or identifies any configuration issues, including policies related to the communication between the source and destination endpoints. In physical path, it provides the details around the path traffic would take between the given endpoints, including source container ID and virtual switch, physical switches, and the destination virtual switch and container ID. Now let's look into the Fabric Analytics. Fabric Analytics extended to have Kubernetes specific dashboard to provide the visibility into the container networking orchestrated by Kubernetes. Kubernetes Analytics dashboard provides the historical representation of all the container events in a time series. Pie chart shows the container network segment. Click on the segment to get the detailed history on container networking specific to that segment. In this case, we see the application containers created for the demo, front-end containers, Redis master and slave containers with timestamp, container event, added, removed, container name, IP and MAC, virtual switch and virtual NIC where it is connected. In summary, Big Cloud Fabric P+V physical and virtual solution with Kubernetes integration enables the dynamic networking for application containers as and when they are deployed through Kubernetes. And BCF also extends visibility and troubleshooting for container networking. Thanks for watching.